Okay, the purpose of this video is to review the concept of ionic compounds. These kinds of compounds are super important in chemistry, and they pop up in a lot of important places, like in a general chem class, in the early section of the book, usually that deals with types of chemical reactions. There are three major classes, which include precipitation reactions, redox reactions, and neutralizations. And ionic compounds play an important role in all three of those areas. And so what I want to do in this video is just briefly review the properties of ionic compounds. All right, the first major issue is understanding how to identify an ionic compound, and the way to do that at the easiest level is to realize that an ionic compound is going to be composed of a metal paired with a nonmetal. Now, one of the most common ionic compounds around would be table salt. And so what I want to do is start the discussion with that. So this chemical formula represents table salt, and you'll see that based on the definition that literally, in a literal sense, the sodium is the metal, and the chlorine, or the chloride actually, to be more specific about it, represents the nonmetal. And the thing that distinguishes an ionic compound from a molecular compound is the fact that ionic compounds contain ions. So they contain ions, and they contain ions of different charges. Now, this is in contrast to something to a compound that is considered molecular. So over here, what I'm going to do very quickly is just give you an example of a molecular compound so you have something to compare to. So this compound represents acetic acid, and what you notice when you look at the formula is that it's solely composed of nonmetals. So there is an absence of ions. There's no ions. Now, coming back to the basic model here, so the formula that represents sodium chloride in the upper left-hand corner of the screen, what I've done is brought in a picture of what the actual crystal of sodium chloride looks like, and what the purpose of this is to give the viewer a sense of how these compounds work. So your ionic compounds, basically what they are vast arrays of oppositely charged particles, as shown by this cube here. And you can see rather nicely how the chlorides exchange places with the positively charged sodiums. And the take-home message here is that for an ionic compound, there really is no unique singular formula for this. And how we end up arriving at this chemical formula is by looking at the crystal and asking the question, all right, what would be the simplest arrangement of these oppositely charged ions that still gives us a sum of zero when we add up the opposite charges of the cation and the anion. And for the sodium chloride crystal, the simplest arrangement that still sums to zero is a single sodium cation combined with a single chloride anion, where the charge on the sodium is +1 and the charge on the chloride is -1, and when we add those together we get 0. All right, so when we look at the formula for an ionic compound, basically that formula is what we call the lowest whole number ratio. So it's the lowest whole number ratio. Lowest whole number ratio of ions that sum to 0. Now, not all compounds, obviously, not all ionic compounds are as simple as sodium chloride. So let's look at some other examples. All right, this is an example of what we call sodium sulfate. And it's composed of, again, to go back to the basic definition, here's your metal. All right, and here is a collection of nonmetals. Now, the sulfate is what we call a molecular ion. So if I isolate this out of the compound and rewrite it, this is what it's going to look like. And it's called a molecular ion because, like the example I drew over here on the right, it's composed completely of nonmetals, and we can actually draw a structure of this thing and show how the oxygens are attached to the sulfur. This is one possible structure of sulfate. So the main point being that this molecule is a singular unit that has a net charge on it of -2. And again, the principle that I talked about over here with the sodium chloride is true for the sodium sulfate. Notice that there's 2 sodiums, and we need 2 of these sodiums in order to cancel the charges on the sulfate, because the sulfate has got a total of 2 negative charges on it, and therefore we're going to need 2 sodium ions in order to keep this entire formula with a net charge of 0 on it. All right, now let's look at another example. This is another ionic compound, and in contrast to the sodium sulfate, this one does not contain a molecular ion. Instead, this is the combination of an iron ion. Specifically, this particular formula is composed of iron 3, so iron plus 3, and it's been paired up with oxide, which is O minus 2. Now you'll notice the subscripts in this formula, which suggests that we need 2 irons and 3 oxygens. Now, in a lot of chemistry classes, the way this is going to be explained is through drop charge. So if we were going to combine these 2 ions to make a singular compound, the teacher would say, okay, well, here's what you need to do. You're going to take this, the magnitude of this charge, and you're going to drop it down over here, and we're going to take the magnitude of this charge and we're going to drop it down over here, and this is how we end up with this formula, which is Fe2O3. But truthfully, if you're in a chemistry course and you're really concerned about doing well in it, then you're going to need to understand how these ions actually combine and why they combine in the ratios that they do. And so let's take a minute to talk about that. All right, so again, I'm going to write down what the actual ions are. So we've got Fe plus 3, and it's combining with O minus 2, which is oxide. So what's important is for the student to realize, again, coming back up here to this crystal of sodium chloride, all right, ionic compounds are not like molecular compounds. They literally are vast arrays of oppositely charged particles. Now, unlike the sodium chloride example, iron 3 oxide is a more complex problem because the iron has a charge of +3 on it and the oxygen has a charge of -2 on it. So you need to think about this. All right, how are these two things going to combine? So we end up with a net charge of 0. So if you look at the Fe+3, you want to ask the question, how many of these are we going to need to combine with the oxygens in order to have a net charge of 0? Well, the common multiple between these two particles is 6. In other words, if we multiply the -2 times 3, we're going to get a net charge of -6. And if we multiply the Fe+3 times 2, we're going to get a net charge of +6. Now, you can see that if we add those two values together, we're going to get 0. So the main point is that we need two Fe+3s to cancel the 3 O-2. So it takes 3 O-2s in combination with two Fe+3s to get a net charge of 0. And that's how we end up at this formula, Fe2O3.